Let's see. We did last time. We talked about hardness as a property. Today we will continue, and we said there are 4 different ways we do the hardness. And we said
دكتور
ايوه
دكتور ممكن بس تعطينا ريفيجن اليوم حق التست ووتر ولا
لا ما ممكن، لا ما عندنا وقت. يوم الخميس ما اخذنا حصه، اليوم ما بناخذ حصه كذي، ما بنغطي الماتيريال. Okay, so let us if you have any questions you can ask later. Okay, so last time we talked about the hardness, and we said the hardness is the ability of the material to resist local plastic deformation, and difference between the hardness and strength basically prevails in that the strength of the material, we say its resistance to global plastic deformation, while for the hardness we say it is the resistance of the material to localized. In this picture, for example, it's localized plastic deformation in a specific region. It's not in the entirety of the material. So that is the basic difference. And then we said we have different ways to determine the hardness, one of which, as we already mentioned, is the Brenner hardness test. We use a 10 millimeter sphere of steel or tungsten carbide. Tungsten is what type of material is this? It's called the refractory metals. Refractory metals have very high melting point temperature, and we can say very high melting point temperature, which means it is a very stiff material there. The bonds are very strong. So basically we put the indenter, which is this now, which is this is the indenter on the material we want to cause the indentation. If you look at this as your material, yani, we push this down like this with a force. We push it down with a force, and with this pushing, as we have already mentioned last time, the philosophy is to push an indenter on the material and try to make an indentation with a specific force, of course. And when you do that, then we remove that indenter, and we look from the top. So looking from the top then gives you the indentation shape which happened. Of course, this is a sphere, it will give you a circular indentation, and we measure the diameter of the indentation, and we need the diameter of the indenter, of course. So, and of course we apply P. P is not variable, it's a value that we apply specifically in the Brenner hardness test, and we can get the Brenner hardness test using this equation, which is 2P divided by pi d times d minus d square root of d square minus small d. The capital D is the diameter of the indenter, and the small d is basically the diameter of the indentation caused by the indenter, and the P is the force that we use. And the way we present that is the Brenner hardness number. So we basically don't put units there. It's a number that we are looking at. Another way of doing that, which is the Vickers hardness test. And the Vickers hardness test, as I mentioned also last time, it is also called a micro hardness test. These both of them are called micro hardness test. Reason why do we call them micro hardness? Because actually, let's say the indentation will be small, and that's why we need a microscope in order to measure the indentation that we do, like that indentation, which we did, but not here, of course, these. And also the indenter is a small, to cause the very small indentations there, basically, and the force which is used to cause the indentation is much smaller than the other ones compared to the Brenner or the Rockwell hardness test, and that's why these are referred to as micro hardness test. The indenter shape is a diamond pyramid in this case. As you can see, this is a diamond pyramid which has 136 degrees. And when you cause the indentation, you push it with a force. Of course, this force in this case is different than that force. It's not the same. That's 136. You push it with a force down there and then remove that and look from the top. It gives you the indentation which is caused there. And then you measure the diagonals using the microscope, D1 and D2, and then take the average of those, and then use this equation in order to calculate the Vickers hardness number. Again, Vickers hardness number. So it's a number, no units will be there. This number has a little bit error there. In the book, you will find it different. You can search in the book for the number there. It's P over D. This is actually the average D between this D and that D square. So basically, this is a simple equation which is used in the Vickers hardness test in order to determine the Vickers number. The third way is called the Knoop micro hardness. And in this case, again, the same as what we have there. We use a diamond pyramid, but the pyramid shape, of course, in this case is different. You can see this is much more, the length of the pyramid is much more in this direction, and width is much smaller. Here we had symmetry. Here we don't have symmetry across the y-axis, as you can see. So when we push it with a force there, indentation like that, from the indentation you can see the shape of the two pyramids are different. And of course we use a different P than that. These P's are not the same. These are the dimensions there, and this is the thickness of the indentation there. And the Knoop hardness number is measured by this equation, 14.2 P over L square. Now L here is the length of the indentation, which you could see there. One question which normally is raised, if I am having specimens, let's say I have results from the Brenner and I have results from the Knoop micro hardness test. This is telling me that for the same material, I have a hardness number, a certain number. And from this test, I have a certain number. Let's say this was 60, and this was given to me 50. Can I compare these numbers and say this is 60 and this is 50, so this says that the material here is harder than that material? Can I do that? Can I compare them? Why not? This is a hardness test and this is a hardness test.
We can't because the standards. We didn't use the same material. Shape different. And
the test, not the material. We use the same material. But actually, this is what he's saying, your colleague is saying, we have the indenter material is different. As you can see, the shape of the indenter, oh sorry, this one. Also this one, you can say the same. So you have a diamond pyramid here, you have a sphere there. The indenter is different shape. So if you have different shapes, like in the tensile test, will you compare cylindrical test specimen results with the flat specimen results? Of course not, because the shape is different. Shape you need to standardize if you want to compare the results. So basically at the beginning, the indenter shape and dimensions are different, right? And the material of the indenter is different. Not only that, but also you have the force that you are using in order to cause. In addition to all of that, the equation that you're using also to determine the indentation is based on something else. So all those actually tell you, no, we cannot compare any of these with any of these. Not only to say that this is micro hardness and this is hardness test, but also in addition to that, you have all the differences which I have mentioned previously. The last method that we want to look at, which is called the Rockwell hardness test. And the Rockwell hardness test, actually it comes with different يعني scales. So for example, we have a scale A, scale C, scale D, scale B, scale F, scale G, and so on. For scale A, C, and D, we use a diamond cone. For scale B, F, G, we use another dimension, 1/16 diameter steel sphere, basically. Here you use a cone, here you use a sphere, here also you use a sphere, but in the EH, you use a different dimension of the sphere. This is enough to say that not only that you cannot compare the Rockwell to the other ones, to the other hardness test that you could do, even within the Rockwell, you cannot be comparing if you do a test using this compared to the test using these, because you need to have the same scale, you see the indenter is different, therefore you will be expecting differences in the measurement. The shape of the indenters are different, the dimensions of the indenters are also different. Not only that, but also the load, as you can see. For the scale A, you use 60 kilograms. For the scale C, you use 150. And then for scale D, you use 100, and so on and so forth. So the scales are different. And within the group of scales A, C, D, you would be using this equation. Within these ones, you will be using this equation, basically. And the T basically is the thickness of the indentation which you have there, how deep the indenter was penetrated, basically, is the value of T. So as you can see, this equation is completely different than this, it's different than that, and different than this. And the loads, of course, are completely different. The shape of the indentation, indenter, the material of the indenter, the force which you use for the indentation are all different, and that's why, again, I'm saying it's not it's not something that you will be comparing. Hardness testing is not it's more or less qualitative than quantitative, and that's why we use a number. It's not very well defined, basically, not like the other test. So we use a number there and not a unit for that. So we say Brenner hardness number, we say Vickers hardness number, Noob hardness number, and then Rockwell hardness number. So R, it's not mentioned here, it will be in the next sheet. So it is RHN. So it's the same thing. So this is a summary of the type of tests which we have, the common types of hardness tests that we have, the most famous ones. Let's just, next will be just summarizing them again or explaining them more here comprehensively, as we have already covered in those. So the Rockwell hardness test constitute the most common test we said last time, because it is very simple. It requires no special skills and kinds of material to be tested. And you can test any kind of material there. It is very simple. To start with, we are starting with the last in the table. So Rockwell hardness test has a diamond cone of a steel sphere with different dimensions. Actually, we do that. Indentation load could go from 15 kilonewton to 150 kilonewton. So as you can see, the load is large, basically, compared to the micro hardness testing. Of course, you will see the Brenner, even we will use forces there. Is determined from the depth of penetration or the indentation. So we use that information, the depth, how much deep the indentation will be caused there. And we normally use initial load followed by a large load. Why do we do that? Utilizing minor load improves the accuracy, basically. Actually, in our lab also, we normally do that, is that we apply, before we do any lab testing, for example, what we do is that we use the machine 1 times, 2 times, in order to make the springs work, in order to move the loads which you have, the weights at the back of the machine, make them move in order to have a good accuracy. In addition to that, we use the machine actually automatically uses an initial minor load. So there is a minor load that it uses, it practices that, it applies the minor load, but then After that, it uses the major load, the real load, which it wants to use to do the indentation. This increases or improves the accuracy of the measurement. The minor load could be 10 kilograms, but then the real loads go more than that, from 50 to 150. It depends on the scale we are looking at. And the major load, you could see, as from the table, you could see 60, 150, 100, and so on and so forth. So you can then start with those. It depends on the scales which we have. The way we represent the hardness number, we could say it's 80 hardness Rockwell based on scale B. For example, this is, you see A, C, D, that is a scale B. This is where we are looking at now. So this is what we have. The B here stands for that scale which we have. Hardness, using 80 hardness number based on Rockwell on a scale B. So it represents the Rockwell hardness of 80 on scale B, which we are saying. Inaccuracies, well, inaccuracies could result in any of the hardness testing machines, and can result from different two main things which could result in the errors in the calculation of the hardness number. For example, you could be having a thin material, and if the material is very thin, then if you are testing the material, for example, you're applying the indentation on the side, you could be actually deflecting the material like this rather than penetrating the material or indenting through the material. So this is actually not a measurement of hardness, therefore. You need to penetrate the material. Therefore, you need the thickness to be, a material to be thick at least 10 times, this is what I'm mentioning here, 10 times the indentation depth. So how much depth of the indentation you need to make? So if you are your depth of indentation is to be this much, you need at least 10 times the thickness there in order not to fall into that inaccuracy. In addition to that, we could also be, for example, if we do it close to the edge like that, even the indenter, if the indenter is thick enough, you could cause also there a deflection to the material and not indentation. And that's why we say also that the specimen should be 3 times indentation diameter away from the edge of the material. So at least, we normally go 10 times at least away from so inside the material, we go at least that much. So these are causes actually of the errors in the accuracy of the measurement. So we can improve the accuracy by avoiding them. The second hardness test is the Brenner hardness test. In the Brenner hardness, a spherical indenter is forced into the surface of the metal to be tested. The diameter of the indenter could be 10 millimeter and is made of steel or tungsten carbide, which is very hard material. The load here is much bigger even than the Rockwell. It ranges from 500 to 3,000 kilograms and 500 kilogram increments. So we could have 500, 1,000, 1,500, 2,000, 2,500, 3,000, like that, any of those. The load is required to be maintained for at least 10, this is the recommendations of the Brennan. You need to keep, when you apply the load, large load there, you need to keep the load for at least 10 to 30 seconds and then remove it. And this is what the machine does automatically, of course. And this is why it is easy. And we don't interfere with the machine actually much, except pushing buttons and sometimes just do the put the microscope lines on the edges of the indentation. The Brennan hardness number is a function of both the magnitude of the load, which we have, the P and the diameter resulting from the indentation, which we saw in the formula, here. So we have the load and the indentation the indenter and the indentation diameters. So the diameter is measured by the microscope. Actually not the diameter here, we say the diagonal is measured by a microscope. Normally this is done in order to be more accurate, and normally the number is put in this way, and the appropriate HB number is found by a chart. So normally we don't do that. We don't use a chart. Because we have the equation. The equation is more handy to just plug in the numbers and find the value. We don't do any of this actually. The machine itself gives us a number, and that is the Brenner hardness number. So this is in the previous times this was done using a chart or using the equation, but nowadays, from long time, the machine itself does the calculation and it gives us a number there directly. So we don't need to do any of this. The Noob and the Vickers, you see I'm putting them both together. Noob and Vickers, both of them are called micro hardness tests. In these tests, very small diamond indenters, of course, they are different in shape. Of pyramidal geometry, of course, both of them pyramid, but again, as we said, they have different dimensions. This indenter is forced into the surface of the specimen. The applied loads are much smaller than the Rockwell and the Brenner. Here we had from 60 to 150. Here we had from 500 to 3,000. But here, as you can see, the loads is from 1 gram to 1 maximum kilogram. That is the time. So the load which we use is much smaller. The impression is normally measured by a microscope because the indentation is small due to the fact that the load is small and the indenter itself is small as well. And then it is converted to a number using an equation. The hardness number is put in this way: hardness K Noob or hardness Vickers. There we read it like that. Both of these tests are referred to as micro hardness testing again methods because of the small loads. Again, I'm mentioning it here, and the small indenter as well size. Again, which I have already explained there, it is difficult to convert one hardness number to another number. So we cannot compare the number when we do a hardness test using Vickers or Noob or Brenner or Rockwell. Compare it to each other, that is not possible. We cannot do that. Hardness number is not a well-defined property. This is what we are saying. Experimental dissimilarities exist between the different tests, and that's why this is not possible to do. One more thing that I wanted to say here is the correlation between the hardness test and the tensile strength, which we said from the beginning of the lecture that both of the tensile strength or the hardness, basically the strength itself, we said it is the ability of the material to resist plastic deformation. And we said for the hardness, if we want to define the hardness, we said it's the ability of the material to resist localized plastic deformation. So basically both of them is resistance to plastic deformation. But one of them local plastic deformation, and the other one is the global response of the material. So it is the global plastic deformation. So therefore, both of them are related to plastic deformation. Both tensile strength and hardness measure material resistance to plastic deformation. So therefore, since both of them are related to that, they must be related in some way as well. So some engineers went and did what? Of course, they looked at the tensile strength of some, and not all, as we say. Some metals are done. Metals can be estimated from the hardness number. How did they do that? They went and they drew. They brought the tensile strength of different materials. For example, for the steel, as you can see, the most important one is the steel. This is the steel there, which passes from to the zero there. So for the steel, basically, this is for cast iron. the nodular cast iron, and this is for the brass. But basically, we are much more concerned about the steel. This has much more application there. The tensile strength of the material, when they plot, they see that there is a straight line relationship as I'm showing there. That is for the steel. So the Brennan hardness number is drawn, it's a number there. It is drawn against the tensile strength. So therefore, we could end up with a relationship, a linear relationship basically, since the line passes through the zero there, and the linear relationship, as we say, as a rule of thumb, for most steels, the Brennan hardness number and the tensile strength are related to according to this equation there. As we are saying, yani y, an equation for the straight line, y is equal to mx, right, plus a constant c. The constant c, if it does not pass, it's not proportional, then it will be passing through the axis there, not through the origin. So since we are seeing that the steel is passing through the origin, that c is equal to 0. So therefore, we have the equation of the straight line, y is equal to mx. M is the slope of the line, so we can look at the slope of the line there. We can determine the slope of this line, which will give us the m. And therefore, very simply, we can determine the tensile strength, which is the y, using the slope if we have the Brennan hardness number. So if we have the Brennan hardness number, we can plug it here. We can approximate, and this is approximate value of the tensile strength, or the other way around as well. If we have the tensile strength, we can always get the hardness number using the Brennan, because the Brennan was used in order to show that linearity equation. So this is for, if we, yani, in a lot of times, you need a number, a rough number, and if you are going to design a machine element, for example, if you're concerned about design, then if you want to a rough, for especially when you're doing a preliminary design, what will you use? Well, you don't need exact numbers there. You need rough numbers, تقريبية يعني, in order to do your preliminary design. Then when you do your detailed design, you see, because the design has stages. You have basically these are the main stages. Basically, you have the preliminary design where you do concept generation, and then concept evaluation. Concept يعني شنو, ideas. So if you want to design a machine element, you want different ideas form in your brain. You do brainstorming, and then you get different ideas, 1, 2, 3, 4, 5, to resolve the problem, or to yani for this need, to satisfy the need. And then in this case, you need rough numbers in order to do comparison between the different concepts yani ideas. When you do that, you need rough numbers there. You don't need to do details, because it will be a lot of work if you do details design for each one of them. Once you finish and therefore you need preliminary numbers here also, yani rough numbers. Once you finished with that, you select among the different concepts there with certain criteria, and you come up with one idea, only one idea there, which you have selected based on criteria of the requirements of the client, of the need, of the stress, of the strength, a requirement of the material, of environmental, of different things. Then you come up with one idea, and this idea, then you do the detailed design. Here you need exact numbers, which yani hopefully the more accurate the numbers will be, the more accurate your design will be as well. This is the end of chapter 6. Do you have any questions? Hello guys.
No, Doctor.
No questions. Tomorrow is your test. Yeah? At 7:30, right?
ايه صح دكتور.
You have your test 7:30 tomorrow. It is a 1-hour test, so from 7:30 to 8:30. When I say no, it's not 7:30 to 8:30. Sorry, I did a mistake. From 7:30 until 8:29. So when you see 29 on your clock, you stop your test and submit. You know the idea. We did this. We had a problem with the quizzes, so good. It was. So we don't want the same problem with the test, because preparing another test will be difficult. I cannot do that. To have the same level of the test, it will not be fair. So I'm not going to do any makeups. Everybody, the date of the exam and the time of the exam was selected by you guys, not by me. And so no excuses there.
دكتور شو يكفي الوقت دكتور ولا بيكون باك يعني؟
This is the point. Yeah, I wanted to raise this here. Since you asked. من انت اللي سألت؟ قول اسمك.
محمد عصام.
محمد عصام. شلونك يا محمد؟ محمد. And all the rest, of course. The time will be given to you just enough to finish the test. If you go back and forth, or if you try to do this or comb your hair, يعني يعني تمشطون شعركم، خلينا نسميها تمشطون شعركم يكون أحسن. إذا بغيت تمشط شعرك وتشرب شاي، تشرب شاي حلو هاي، لا؟ إذا بغيت تشرب شاي وتمشط شعرك ما بيمديك وقت. You will not finish. So don't comb your hair, because we are recording here, and don't drink tea. No, don't do any of those. If you do that, then no, or chat with other guys, يعني. You will not be able to finish. The time is given is just enough. You have lots of questions to do, so you need to don't rush, and don't be يعني wasting your time. خلص امتحانك، لا طالع يمين لا طالع يسار. هاي مهم. This is number one. Number two, there is one question in the whole test that I am giving you. You need to solve it on a paper. الجواب تحطه على ورقة، تكتبه بالقلم يعني، and you upload the file. واضح؟
دكتور الحل يكون في الورق مو بأونلاين يعني؟
لا، الحل مال الامتحان كله بيكون اونلاين. سؤال واحد بس ما اعطيكم اياه تسوونه على ورقة، تحلونه على الورقة، بس سؤال واحد. And it is one file that you can upload only. And this file is small, يعني it should be not more than 10 megabyte. Okay? سؤال بسيط، أنا في كذا فرع له يعني. هاي السؤال you solve it on a paper, picture it and send it and upload it to the system when you're doing that. واضح؟
واضح.
حتى مشكلة الشغلة راح تاخذ وقتي.
نعم.
ايه يعني نحل باللابتوب.
ما عليك لست انت. اقول لكم بعد. Okay, keep. What is the timing here? أنا مضطر أوقف التسجيل لأن طلاب الثانيين بيقولون وايد وقت.